Hello and welcome to my presentation. First of all, I hope that you are doing well and that all of you are in good health. This presentation, I will explain how by using subset selection techniques and edit distance, we can approximate the conformance value in a faster time. The other authors of these papers are Dr. Van Zels and Professor van der Aalst. Conformance checking is one of the main subfields of process mining. By conformance checking, we aim to detect how real event data are deviated from designed or sometimes discovered process models. So we assume that we have a model and an event log. There are different ways to show a process model. Here we use the PetriNet notation to show a process model. In this slide, you also can see an event log with 20 traces. It contains 5 unique trace variants that the most frequent one has 10 traces. There have been some different techniques to compute the conformance checking. For example, using footprint and token replay. However, nowadays in both academia and industry, we use alignment technique for conformance checking. We can consider a process model as a set of traces that can be replayed by it. Of course, if there is a loop in the model, it could be produced in an infinite set of traces. So set of all possible traces could be infinite. Compute alignment of each trace in the log with the model. We should first find the most similar trace in the model to the log trace. Thereafter, we compute how these two traces differ with each other. To find the most similar model trace and also to compute their distances, we can use different measures. Here we use the adopted version of Levenshtein distance that we call it as edit distance. It simply measures what are the minimum number of insertions and deletions that require to transfer one trace to another trace. For example, suppose that we want to compute the alignment cost for trace log AE with this model. The most similar model trace to AE is ABE. We can transfer AE to ABE by inserting B between A and E. Therefore, the distance of them is 1. We use the minimum distance according to the following formula to compute the fitness value. The denominator is the sum of the shortest path in the model or the shortest trace model and the length of log trace. So the length of AE is 2 and the shortest path in the model is 3, and consequently the fitness of AE and the given model is 0.8. Of course, we can compute the fitness of a whole log based on average of its fitness, fitness of the trace variance in the log. Unfortunately, computing conformance checking using alignment technique is very slow and sometimes inapplicable for big real event logs using normal hardware. There have been some approximation methods provided to improve the performance of alignment. However, some of them couldn't provide any guarantee for the approximation value, and some of them couldn't really improve the performance for some event logs. The outline of remaining part of my presentation is as follows. First, I will explain our proposed method and the experimental results. Afterward, I will provide the conclusion with some future directions in this area. As I explained, a process model could be seen as a set of possible traces that could be replayed by the model. The point is, for real scenarios, this set could be very large and sometimes infinite. And consequently, finding the most similar trace among them will be very time consuming. Therefore, our main contribution in this work is to consider a subset of traces among them. So we just select a subset of all possible traces that could be replied by the model, and we call it MB. Note that when we use MB instead of all possible model traces, we may provide a lower bound value because maybe the most similar trace is not placed in the MB. However, the fitness value that computed by MB is a lower bound for real fitness value. So the first question is, how could we have this MB? How we could build this MB? There are two main methods for building MB. We can simply just simulate the model and keep as much as traces that we want, or we can select some of the log traces and using the normal alignment techniques to find the most similar traces of them and consider them as MB. Another question is, which log traces should be chosen for computing their alignment if we use alignment technique? There are many subset selection techniques. However, in this work, we propose three methods in this regard. First, we can use clustering and cluster event logs to K clusters. And for each cluster, we select the most representative trace variant. Another way is to select the K most frequent trace variants, and we can also select the trace variant based randomly. Note that the size of MB and selected traces affect on the performance of conformance checking and also its accuracy. So if we use alignment method to compute the MB, we need to first separate the event log to selected and unselected trace variants. Afterwards, for selected trace variants, we compute the alignment and consequently build MB. We also keep the average fitness value of them because we are sure about their values. For unselected traces, we use MB instead of whole traces, whole process model or whole possible traces in the model. As explained, the computed value will be the lower bound for the actual fitness value. For approximating the fitness value, we compare the lower bound with the average fitness that is computed by using the normal alignment technique. And we consider the maximum value for them. Note that we can also provide an upper bound for the real fitness value based on the shortest path in the model. So if the length of trace is shorter than the shortest path in the model, we know that it needs some insertion at least. However, if it is not shorter, we couldn't do anything for the upper bound, and we simply consider 1 as the upper bound of that trace. To give an example, in this slide, we are able to approximate the conformance value for our example event log and the process model. Suppose that MB is ABE and ABCE that could be simply generated by computing the alignment of the first two frequent trace variants. We can compute the bonds and the approximation for different traces, and you can see it in this table. For example, for trace ACBDE, that is the third trace, the most similar trace in MB is ABE with cost 2. Note that there are two more similar model traces for ACBDE with cost 1. However, they are not appear in the MB. So they are not presented in MB. So the lower bound is 0.75, and consequently the approximated value is 0.857. That is the average fitness of the first two variants, because we compute them based on alignment. To evaluate the proposed method, we implement it in the PROM platform and apply it on 8 real event logs. Some of the event logs are big, and some other, like sepsis, have several unique variants. For process models, we use the inductive miner with 3 different noise thresholds. We also use the alignment to provide MB with different percentage of trace variance in the given event log, and we call it the approximation parameter. Our research question is, our research theory is, by increasing the size of MB, we could have more accurate and also have less performance in the approximation. Moreover, we compare our method with one existing approximation method that uses statistical sampling for this purpose. Here you can see how, using approximation methods, we are able to improve the performance of conformance checking. Note that in this figure, we consider the pre-processing type that is corresponding to the time that is required to select trace variants. This pre-processing time is high for the clustering method, but for example, for random selection, it is very low. We can see that by increasing the approximation parameter, the improvement is reduced in most of the time. We can also see that the statistical sampling method is not able to improve the performance of conformance checking for some event logs like sepsis, that because we have lots of unique trace variants there. Note that the instance selection or variant trace variant selection is independent from conformance checking. For example, we may select the traces before conformance checking process. In this slide, you can see the performance improvement without considering pre-processing time. You can see that using this approach, we are able to improve the performance of conformance checking more than 100 times for some cases. It is shown that the highest improvement is for the simulation method. In this slide, we can see the average accuracy of approximation for conformance value when we use different approximation methods. As explained before, we use different inductive miner thresholds for process discovery. To compute accuracy, we simply just considering absolute difference of actual fitness value and the approximation value. In this table, the darker green means a higher accuracy compared to other methods, and a darker red means the worse accuracy. We see that the simulation method cannot provide accurate approximation for most of the cases. However, for process model with a smaller set of traces or simple process models, the simulation method provides completely accurate fitness value. We can see that the statistical method is able to provide accurate results for most of the cases. Moreover, in several cases, we can see that clustering and frequency-based methods have reasonable accuracy. Note that here we show the average accuracy values. We use different approximation parameters and consider the average value here in this table. By increasing the approximation parameter, we see that we always improve the accuracy using these methods. In this slide, we can see how by increasing the approximation parameter, we decrease the bandwidth. Bandwidth is a difference between the lower bound and upper bound. For some event logs, the bandwidth is high. That is, for some event logs, the band width is very high, so that is not very suitable. We're really interested in bandwidths that is close to each other. It is not possible. It is, so the reason is not because the complexity of models. It is more because of the presence of different behavior, different trace behaviors in the event logs. We can compute how different traces in logs are similar to each other in the table below. By knowing this, we can have a good estimation before doing conformance approximation. For example, if the log has very different behaviors, it is expected that we need to use a higher value for the approximation parameter. So it somehow gives some feedbacks to the user for selecting a good approximation parameter. As explained, our method is able to provide bounds for the approximation. In addition, it can also return the deviation rate of different activities. You can see the formula of deviation rate here. Note that the asynchronous moves correspond to insertion and deletions that are needed. Here in this table, we return the most 6 problematic activities of each log and compare their deviation rates with our method compared to the case that we use the normal alignment. In most of the cases, our method spots the problematic activities correctly. To conclude, we propose an approximation method based on subset selection and edit distance for conformance checking. The proposed method is able to provide bounds for the approximated fitness value and also show deviation rates of activities. Using our method, we can improve the performance when we have a reasonable accuracy. It is shown by experiments that by increasing the approximation parameter, we will have more accurate results. However, if we, for example, increase the size of MB and considering all model behaviors, we couldn't have any improvements. So the user could balance between performance improvement and the accuracy of approximated value. To extend this work, we aim to provide an incremental conformance checking that incrementally increase the size of MB and show the bandwidth for the approximated value. And user can stop the incremental process when the bandwidth is enough for him, or if the accuracy is enough for him. Moreover, we aim to improve the simulation method to have more accurate results, because we see that this method has a high performance. However, its accuracy is not good enough. My presentation is finished. Thanks again for your attention. Please feel free to contact me if you have any question, or if you want to discuss more about this research, or if you have any ideas to extend this work. Take care and stay safe.